In this video, we're going to talk a little bit about how to change from rectangular to polar coordinates in a double integral. So when we're setting up a double integral, we have a choice between using rectangular or polar coordinates. Now, it may turn out that one system might be easier to describe the domain and to set up, therefore, to set up limits for the inner integral. Or it may be that one system may produce an integrand for which it is easier to find an antiderivative. If an integral is already set up in one coordinate system, then we may benefit in one of these two ways by either making better limits on our integral, or by having something that's easier to find an antiderivative for. In one of those two ways, you might benefit by switching it to the other system. So we should remind ourselves about the relationships between polar and rectangular coordinates, and it's all given by this basic triangle you see here illustrated. This side is x, this side is y. It's a right triangle. This angle is theta, and this side is r. And we get basic right triangle trigonometry relationships here. The cosine of the angle is adjacent over hypotenuse, so that's x over r, which, solving for x, we see x as r cosine of theta. Similarly, y over r is the sine of theta, and so y equals r sine of theta. We have a Pythagorean relationship here, x squared plus y squared equals r squared, so r is the square root of x squared plus y squared, at least if you're picking a positive r. And of course, tangent of theta is y over x. And we can, by picking certain thetas, we can use this to solve for the infinitely many possible thetas that we might have. So we can use these to convert formulas. Anywhere we have an x, we could replace it by r cosine theta. A y, we could replace by r sine of theta. Anytime we have an x squared plus y squared, that could be replaced by r squared, or the square root of x squared plus y squared could be replaced by r. And y over x is tangent of theta, and so forth. So we can use these to convert formulas. So for example, let's look at the following integral. Let's evaluate this integral. The double integral from 0 to, that's supposed to say 2 there. So the x's go from 0 to 2. The y's on the inner integral go from 0 to the square root of 4 minus x squared, and the integrand is the square root of x squared plus y squared. Now we might be able to work this integral out just like it is, but it's going to be a little bit nasty because the thing we have to find an antiderivative for has a square root in it. That might involve something like, maybe a trig substitution or something like that. That's going to be a little bit more difficult. No telling what's going to happen with the second integral when we put this function in there. That might make it worse, might make it better, we don't know. But this one actually turns out to be very nice if we change it to polar coordinates. And one of the things that sort of is a giveaway is the integrand is very nice. You should recognize that as just being r. And we need to see what that region is. So there are three things that we have to do. We have to graph the region and figure out what the appropriate limits here are for r's and thetas. We have to convert the formula of the integral. So we're going to be changing this formula. We have to be changed all of these things here, all four of these things. And then we also have to change this differential dy dx to d theta and dr, but if you remember, dA is dy times dx, but it's also r times dr times d theta. So we have to insert that extra r there. So remember that you have to do all three of these things. Don't say just do the first two and forget to put that r in there for the third one. You have to do all three pieces. Well, when we describe this region here, it's actually not too hard to see. When we have y equals the square root of 4 minus x squared, square both sides, we have y squared equals 4 minus x squared. Add x squared to both sides, we get x squared plus y squared equals 4. At that point, you should recognize that that's r squared equals 4, or just r equals 2, a circle of radius 2. Actually, it's only going to be a quarter of that circle, as it turns out, but that boundary curve is that circle, or part of it. When we run this from y's going from 0 up to that curve, we're below that, and it's the positive square root, so it's the only upper semicircle. But then we only do it from x's going from 0 to 2. So we're looking at this quarter of a circular disk is our domain. And so that makes it, that's this really nice and easy to describe this kind of a region in polar coordinates. Furthermore, as I already pointed out, the square root of x squared plus y squared is just r. And then you have to remember that dA is dy times dx, but it's r times dr d theta. So I replace the dy dx by an r dr d theta. This is replaced by r. The two r's multiply together to get the r square here. Now, if I integrate with respect to r first, we would take a radial line segment from the origin out to this curve, and no matter where we go, all the way as we sweep the angle around here, it always starts at 0 and goes out to this curve, which is just r equals 2. So the r's just go from 0 to 2 no matter what. And the thetas, as you can see, are going to go from 0 to pi over 2. So this is especially nice because this is just constant limits of integration here. And this is a pretty simple function. So you can see that we've simplified this a lot by changing to polar coordinates. Now let's go ahead and figure it out what the integral is to finish this up. So this was our original integral. We converted it to this polar integral. It was originally in xy or rectangular coordinates. Now it's in r theta polar coordinates. Well, we take the integral, our antiderivative with respect to r, that's just 1/3 r cubed for an antiderivative, and we evaluate that from 0 to 2 for the inner integral. The 1/3 I brought all the way out front of that and out front of the integral sign. And this is just 2 cubed minus 0 cubed is 8, which I also brought out front to make that 8/3. The antiderivative d theta is just theta. Evaluate from 0 to pi over 2 is pi over 2 minus 0, which is just pi over 2. Pi over 2 times 8 is 4 pi, and so our integral is 4 pi. And it is pretty much easy as pi if we do it that way. Whereas if we had tried to do it directly in rectangular coordinates, it would have been much more difficult.